Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good afternoon, everyone. So I'm very happy to have Mateusz Telgarski from University of Michigan. So many of us are interested in deep learning and trying to understand what are its theoretical underpinnings, and Mateusz will try to tell us something new about those.
Hi, thanks a lot, and I'm very happy to be here. It was very nice to be invited by Sebastian, and I'll also say that I like this topic very, very much, and not just because it's become popular, but actually I think there's a lot of just independently interesting things about this problem, and I think there's a lot for basically everybody to contribute to it, just from almost any standpoint, even just a purely mathematical one. So before I tell you what's in the talk and any sort of summary, most of this talk will be first principles, so I'll just tell you even what a neural net is, and specifically the kinds of neural nets we'll talk about today. So a neural net is just a way to write a function as a graph. So it's a computational graph that works as follows. So the graph has some kind of multivariate input, and then there are nodes. And they're computational nodes. The way they work is they collect a vector from all of their parents. They wait for their parents to compute something. Then they perform a linear combination of what their parents did, and then they apply a fixed nonlinear function sigma. So a class of neural nets, the way it's defined is we fix the network layout. You've noticed I left out some edges. So it's just some collection of nodes and some collection of edges. That's fixed, and the sigma is fixed. What we vary are these linear combination weights. And one of the standard choices for this nonlinear function sigma is this funny function, which is identity on one side and 0 on the other side of 0. So this function's actually become very popular lately. It's kind of the most popular one right now. And when I started thinking about this problem, I thought, well, I might as well just try to get caught up and use this one because it's popular in practice. But fascinatingly, this was actually beautiful to work with mathematically. So this will be the nicest one for us to work with today. And if you follow any of this literature, there's all sorts of other words people use to describe the kind of fanciest, most complicated versions of neural nets that are popular. And we won't be discussing those. These are words like pooling and convolution. We won't be discussing that today. So this is just a very simple version of a neural network. OK. So this is what the talk will cover. We'll try to get a handle on exactly what this class of functions is, because I've just defined it symbolically, but it's not at all clear what these actually look like as I vary all these linear combination weights. So we want to understand what these actually look like, what this class of functions is. So I'll first cover a classical result, which is that they can fit continuous functions. And this result has a very strong limitation in the sense that it does not tell us anything about what we gain from having multiple layers of these things. So in practice, and especially lately, people build these very deep circuits. But these classical results only say something about, in fact, something with only 2 layers. So because of that, we'll talk about 2 results that do tell us a little bit about the benefit of depth. So one is one of my personal favorite results in actually the entire machine learning and statistical literature, which is the computation of VC dimension of these functions. And don't worry if you don't know what that means. I'll also explain what VC dimension is. And then the second one is what I call exponential separation. It's basically a case where if you allow yourself to have multiple layers, then you can get away with using exponentially fewer nodes or logarithmically as many nodes. And so this is, in terms of hype, this is the new result, if you want to call it that. But on the other hand, it's actually, as I'll say in the closing remarks, when I give a lot of open problems, the new result is actually I'll tell you guys, it's actually the wrong result. It's not nearly what we wanted to prove. So the problem is still very open. So like I said, there's lots of room for everybody to contribute to all of these things. OK, so just to warm up and start this whole setup very slowly, when I say that we're going to fit a continuous function, I have to say what fit means. So one of the standard ways to say we fit a function is in the LP sense. So If you're familiar with it, this is an LP norm. And it's just basically an integral. And the point is that often we would like this uniform sense, which means for every point in our domain, we are some epsilon away. This one's a little bit weaker. We can average so that we can give up entirely on some small regions of points. So this one's easier to satisfy. This one's harder to satisfy. Oh, and there was little pictures. So that's kind of the average sense, and this is the uniform sense. And then in the later sections, we'll actually care about what I'll call the classification sense of fit, which means there's a problem we want to classify, and we're going to care about how close we can get to classifying correctly on this problem. OK, so continuing the warm-up theme, let's just cover a very simple, kind of the simplest possible setting. So what if we only have one layer? And of course, if we only have one layer, and I'm only doing a univariate prediction, so this is really just one node. It's a neural net with one node. What can we fit with that? OK, it's a simple question, and it has a simple answer. If this function sigma is monotone, then basically, if it's monotone in this linear combination, I almost have an indicator on a half space. There's some half space, and I'm going to be going up basically along with the normal vector of that half space. So another way to say that is I clearly cannot fit arbitrary continuous functions because consider this one. If I'm correct over here, I have to be small over here. So that means I'm large over here. So if I'm correct on this, I'm wrong on either of these two. If I'm correct on one of these two, I'm wrong on this one. So this kind of a direct argument tells us that in either of the sets of fit, we have to make a pretty substantial error. So this was kind of maybe a stupid, trivial example, but there are two reasons it was valuable. So one is we proved that one layer is not sufficient, and it's going to end up that this is actually tight. So with two layers, this is all we're going to need. And the second thing is that in this lower bound, we had a function that basically has one bump. We have this half space and a monotone function on it. So we're basically fitting something with kind of one bump. And it's going to happen in all the results today that if we build a shallow network, we basically need to have the same order of nodes and number of bumps in the function. So this principle will drive all the lower bounds today. OK, so to make things a little bit more interesting, let me tell you about one of the I consider this to be the folklore proof of how powerful a neural net is. This isn't quite as strong a result as the standard one people throw around to say that neural nets fit in a continuous function, but I personally find this result to be extremely illustrative. So let's say you want to fit a continuous function from 0, 1 to the d, so the hypercube, to just 0, 1. And in this picture, I've made it even easier. I have the thick red regions are supposed to be where the function is 1. So it's 1 in those regions, and it's 0 outside. So if I wanted to fit this with a neural net, I claim that it's trivial if I can fit a box with a neural net. So by box,
sorry, I didn't say. What was the continuous function?
Oh, so you mean in the picture, or?
Yes.
So it's from the interval it's from 0, 1 squared. So it's from the plane.
Right.
And then I've just drawn the level curves. So the two thick red.
So it's one inside the.
Yeah.
Yeah,
Okay.
sorry. It's 1 inside here, 1 inside here, 0 out
So you
here.
have some decaying thing near the boundary, otherwise it's not. That's right.
Yeah.
So you have to.
Yeah, I was just trying to simplify the picture. Sorry.
So near the boundary, it goes from 1 to 0 in a continuous fashion.
Yeah,
Okay.
very quickly.
Okay.
It's a thick line, I guess.
Yeah, you could call it an ISO line, and I was just at scale 1. But
Okay.
yeah, somehow drawing pictures is difficult. Sorry, but so if we had a neural network that could L1 fit a box, and in the LP sense fit a box, then I claim this problem is trivial. And the reason is we just grid the space, and we just fit each one of those boxes, because then we can just add these all up. I can add things up. I can take linear combinations through a neural net. So I've reduced the problem of fitting this function to just the task of fitting a box. And let me just say there's kind of a common theme that'll come up here, which is that I'm building basically a gadget out of a neural network. I'm going to have a little tiny neural network that fits a box, and then I'm just going to look at the span of those things. So I just like calling it a gadget. OK, and to fit a box is also very easy for us. So just suppose that this nonlinear function sigma is very close to the indicator function. We're going to say how to fit it with just 2D plus 1 nodes. And the hint as to why it's 2D plus 1 is because a box is an intersection of 2D half spaces. So because these neural net single nodes behave roughly as an indicator on a half space, got 2D half spaces. So what I can do is I can just take one dimension, and I can put one of these. I can put one function with each of these normals, or along each of these normals. So it's 2 in here, and one in each of these. And I can do this for all of them. I end up with this. And now I'm in good shape, because if I just apply one more, and I can threshold at 2D minus a half, and so only this region will be satisfied. So basically, it's just intersecting together 2D half spaces. And then that's kind of what you get after that. So with this kind of fuzzy reasoning, we fit a continuous function from 0, 1 to d to r with 2.5 layers. I say 2.5 because I'm just using the linear combination part of the neural network. So with 2 layers, I fit a box. And then the span of these can fit any continuous function from 0, 1 to the d to r. And then if I apply another nonlinearity, then I'll be at 3 layers. But then I can't fit any. But then my image is constrained to be 0. My range is constrained to be 0, 1. OK, so this is kind of the folklore result. And so there are a couple problems with it. So one is that, as was kind of pointed out, because everything is continuous, we have a lot of fudge factors on these boundaries. I can't exactly do these hyperrectangles. I have a little bit of fudge on the ends. And so that's why I have to do an LP type fit, because I have to allow myself to kind of make some errors on the boundaries. If I wanted to do a uniform fit, then in the supremum sense, then I wouldn't be able to use this argument. It wouldn't work. I also want to say how old this proof is. I consider this proof to be as ancient as mathematics, basically. If you look at Jordan content or definition of Lebesgue integral or any of these things, you see these kinds of box arguments. I'll also say that notice the way the proof worked. I claim that we really didn't use anything about composition of functional neural nets. I built up a basic class of functions, and I looked at its span. And so in fact, if you look up how to prove, for instance, that boosting is consistent, the AdaBoost algorithm or whatever you call it, then one way to do it is to take decision trees of a certain size. If you make them have 2D nodes, then they can fit boxes also. And so the same proof says that boosting can fit arbitrary decision surfaces. So again, this is only a vector space argument. It is not an argument using anything about composition of functions. We constructed a basis class, then we reasoned about its span. OK. And so we had a gap. We had 2.5 layers, the upper bound. We didn't have a uniform fit. And so we have a gap between this and the lower bound. So we can close this gap with the so this is the result that everyone actually cites when they say neural nets can fit any function. They cite this result by this guy, George Sabenko, from 1989. And I don't know how it is for everybody else, but even though I see this cited basically infinitely, it's like in every paper, I've actually never seen anyone discuss it, just for reasons I can't really comprehend. So just like comment. But I actually like this proof a lot. It's extremely clean, and every bug that you and every little kind of nastiness and sloppiness and everything I just said is gone from this proof. So, and I will say that I'm watching the clock, and so I'm going to rush. Screw it. I'll just give the whole thing in detail. It's fine. It's very clean. So the setup of the proof is very similar to the last one. I'm going to build a gadget. I'm going to build some kind of primitive object out of just neural net nodes. And I'm going to reason about the span of this thing. And before, I kind of used very hazy reasoning. I said fit things with boxes, grid the space, Jordan content. But we don't need to do any of that, because vector spaces are such well understood objects that I can just, there's theorems I can use. I don't have to say, approximate things. So the proof itself is all using functional analysis. That might be why it's not discussed much, because the way it's stated is actually maybe a little bit impenetrable. But I'm actually going to give a Hilbert space version of it. And the Hilbert space version, you can just read it knowing what a vector is. If you know what a vector is and what Pythagoras' theorem is, you can just understand the proof. So, OK. So here's the proof. The first step is you prove that a single neural net node is what I call a correlation gadget. And I left something out of this slide. I have to tell you what sigma is. All we need for sigma in this proof is that on one side it limits to 0, on one side it limits to 1. The whole function is bounded and measurable. It's all you need. It can be 0. You can do any stupid thing you want, and then it can go to 1. So it's an approximation of the indicator, but it's a very weak approximator of the indicator. So you have to believe that this, what I call the correlation property. So give me an f that's non-zero, continuous f that's non-zero, and f it has to be an L2. It has to be an L2 function. But give me an f, then if it's non-zero, then there exist choices of the linear combination parameters so that this integral is non-zero. So for any non-zero function, I can kind of detect some structure in it. And interestingly enough, the proof uses basically the same box-fitting argument I gave earlier. The effective way the proof goes, it says if the function is continuous, then I can kind of build up boxes. I can integrate the function using boxes. But those boxes have to have non-zero measure, otherwise the function is 0. So the proof of this actually embeds the previous proof. Technically, it has to use Fourier analysis, but it's the same. It's using the same thing under the hood. So this is a lemma. And then here's in the Hilbert case, it's just almost a direct argument. So I have all of these. So these correlation gadgets, these are just all the functions here as I vary W0 and W. So I look at the span of that. Okay, so that's a subspace. I'm in infinite dimensions, so it might not be closed. So I take the closure of it.
So closure in the
L2 sense. Yeah, this is one of the places where in the full proof, you have to work in the uniform topology and this kind of, I guess. So anyway, so it's this closure, but now it's a closed subspace. It's a closed subspace, and I'm in Hilbert space. I can talk about things like perp vectors, Pythagorean theorem, all this kind of stuff. So the theorem will be that the closure of the span of these things equals the continuous functions. By definition of closure, this means that for any epsilon, I have an element in here that is epsilon close. So the proof goes like this. So I say, give me any continuous function, and I can project it onto my closed subspace. And then I can just look at this difference. I can look at the difference of the two.
This implies that the continuous functions are closed in L2.
Sorry? I didn't hear.
So this implies that the continuous functions on 0, 1 to the t is a closed subspace of L2?
No, it's just.
It is not. So what you can say is the continuous functions is a subset of this closure, but this cannot be inequality.
No, but any continuous function, they're dense enough.
Right.
It's just.
I'm talking about the L2 continuous functions.
So, but the closure is in the topology of the Hilbert space, which is the L2 closure of some subspace.
Yeah.
If that has to be equal to the set of all continuous functions.
It's not the set of all continuous functions.
That is the statement there.
This is I'm giving the weakened version of the proof, which is only for Hilbert spaces. I'm not giving the whole uniform version of the proof.
So I don't understand that statement. That equality there, which is the closure of that span, equals what?
You're right. I should have justified the right-hand side with only Hilbert spaces. But so the full statement uses the uniform closure and the uniform topology.
The pesky thing is the continuous functions themselves are inside the Hilbert space. Yeah. They're not the Hilbert space because it's not complete.
Yeah.
But it is inner product space, so you can do a closure in there.
Yeah, since I see that.
Okay.
We can move on.
Yeah, okay.
Yeah. Well, what I'll do is after I state, because it's clear to me that you understand this very well. So after I give the Hilbert version, I'll tell you how to translate all of the lines into the function analytic version. This was
designed for a different audience.
Well,
Less picky people.
No, this is the audience I always want to. I mean, this is great because I have a background in I use functional analysis myself. I have to ask myself at some point why I so rarely see the details of this proof discussed. And the only thing I can come up with is that people get scared when they see the phrases like Hahn-Banach theorem, and they have to, this thing, for instance, in this proof, so you said it used Fourier analysis, but you have to take Fourier transform of a measure, not of a function. And so this already is something that, for instance, isn't well covered in my grad analysis textbook. So, but you are right that in this case, I left out too much detail and that equality doesn't hold. So I apologize for that. That aside, let me just say how the rest of the proof goes. So now let's look at this thing. So I know that f minus g is orthogonal. It's in the orthogonal complement to this subspace S. And that means that the inner product between this and every element in S itself also has to be 0. But then I can use the contrapositive of this. If that's 0, that means that for all of these, that's 0, which means that there's nothing outside of, that means that my perp is 0 itself. Every perp element evaluates to 0, so that equality holds. So now that that's been said, let me explain just quickly for the experts in the audience how to translate this thing into what it actually is supposed to be. So I don't use the L2 space, but I use this, the correct topology for continuous functions is the set of continuous functions, by the way, under the restriction 0, 1 to the d, 2 r. That's important because it's important that I'm talking about continuous functions over a compact set. So this together with the uniform norm, which is that sup norm. So that is a Banach space. And the important thing is that the dual of this space is the set of Radon measures on this thing. So Radon sign measures. And so then this step, so we cannot take projections, but I can use the Hahn-Banach theorem to get what's effectively a perp vector. And so then I can still use the same reasoning over here. So no, that was an excellent point. And okay, yeah. I feel very bad that yeah.
No, don't feel bad.
Okay. All right. So this is the quick summary. So 2 layers is enough in a very strong sense, the cell infinity sense. And also notice what we actually constructed in this theorem. These correlation gadgets, this is exactly what you're doing in boosting algorithms, for instance. You basically find the weak learner which is most correlated with the thing. This is an algorithmic proof. You greedily, you wouldn't, if you're constructing this fit, you would actually pick the most correlated thing every iteration. And so this has been done. This is actually what I would argue popularized to a great extent these greedy methods. This is a big paper by Andrew Barron from 1993. And just a funny remark, we can fake make this algorithm deep in the following way. I can take a deep network where what it does, it devotes part of every layer to copying the input forward. And so then I can just, every time I would do my boosting type thing, I would just have the nodes just kind of go like that. And while this is kind of stupid because that means I have, D nodes in every layer doing the copying, maybe there's some way to compress it and get something nicer. Okay. The problem though with this is that there's not a good understanding of the number of nodes and number of layers trade-off, or of function composition in general. So we haven't. It's nice that this result is true, but I really like the Sabenko proof, but we have not really gained that much about the heart of the problem. So the next section, like I said, are results very dear to my heart, and because I've slowed down a little bit, I'll just kind of state the highlights here. But I will say again that these are absolutely beautiful results, and I find them personally very surprising. So I'm just going to assume everyone knows what VC dimension is. So the question is, so now that I gave you these networks, and so suppose that in those networks, every one of those sigmoid functions is just the indicator 0, 1. So the question is, what is the VC dimension? And for me, the fascinating thing is that it's literally ignoring the log factor. It is just the number of parameters. So it's this first one. And this to me is interesting to think about because a simple perceptron, so only one node, is also theta of W. Now, this one is actually, this one's W log W. W is the number of parameters in the network, so all the edges, for instance. So this schema where I use that function like just an indicator, it doesn't reflect the structure of the nonlinearity whatsoever. Okay. The proof is actually kind of a straightforward induction. Now, if I allow these, that I said, these kind of popular nonlinearities now, the VC dimension changes. And not only does it become just the number of parameters times the number of layers, the theta was only closed by Peter Bartlett, and he hasn't even typed it up yet. If you look in his book, it's not completely nailed down yet. So this is already fascinating to me that it only increases just multiplicatively by the number of layers. So I personally find this quite fascinating. And I have to say, not only do I think the proof is beautiful, but I would argue that Bartlett himself loves the proof because the proof is actually the cover of the book. I'm actually serious. I'm not making this up. This might look like some kind of stain, some kind of radioactive staining of a neuron with like axons or something. It's actually not. If you look in the book in chapter 8, the figure appears, and he just kind of doodled on it to make this. I haven't asked him about this yet, but literally the proof of how this works is in there, and this is an amazing proof.
So, Matush, in general, the VC dimension is going to be at most the number of parameters squared if you have a sigmoid. If you have something that...
If we do not have a bound on a number of layers, the only upper bound we know right now is W squared, yes. But for these piecewise, well, it ends up being piecewise polynomial, if the sigma is piecewise polynomial. As we change what sigma is, all sorts of terrible things start happening.
What I just said is true for piecewise
yes.
polynomial. Okay.
Yes. I'll just say one brief thing. You might say, I'm sure regularity assumptions hold. So let's make sigma concave, convex, goes to 0, goes to 1, and I can impose a smoothness bound on it. Turns out I can choose one of these to get VC dimension infinite with only 3 nodes. So this is a very delicate business. And how do you actually prove these VC dimension bounds? You have to use really high-powered techniques. So for those of you in the audience that know Sard's theorem and know Bezout's theorem, so Bezout's theorem talks about counting intersections of polynomials in high dimensions. And it starts to make sense why that would come up. So these proofs are amazing. So if you do have time after or later this week, you can ask me because I love all these results a lot. OK. So what we know so far is that a flat network can fit any continuous function. And we also know that the number of functions we have in the classification sense, how many classifiers we get, it doesn't actually grow that fast with the number of layers. But what we don't know is what these functions actually look like. So in an attempt to get a sense of what the functions with many layers look like and how different they are with what you can get with a flat network, I asked and answered the following question. So the setup is as follows. You give me an integer k. So this is going to be a result that holds for all positive integers k. You give me a k. I can construct 2 k points with the following property. Any flat network with less than 2 k nodes in the network will have error at least a sixth. And the result itself will quantify what flat and all these things mean. There are no, it's actually not even going to use asymptotic notation. It's a very clean, easy to prove and easy to state result. And it's not just a separation from flat and deep. It'll be for any arbitrary number of layers. And then the punchline will be that if you give me, it ends up 2k layers, I can get 0 error with just 2k parameters. And something called a recurrent net, which is a fixed small network, so a network of constant size. And then I take its output and plug it back into itself. And I do this k times. It'll also get 0 error. And the reason why I care about this, in addition to just understanding this class of functions, is because in a statistical sense, I know that this thing has exponential the VC dimension of this thing. So maybe there's some hope for learning these functions from data well. And the thing to contrast this against is the switching lemma and related circuit complexity results, which get a similar trade-off. So yeah, I'll talk about this more maybe offline. OK. So let me tell you what the class of sigmas that I deal with is. Actually, yeah, OK, I'll just do this. So this is just a class that has two nice properties. It'll slightly generalize that constant and then identity function. And also, I can use this class of functions to inductively reason about what every layer and every node of the entire network is doing. So that's why this will be a convenient class to work with. So I call this function t sawtooth. If it has t pieces, so I take the real line, I partition it into t intervals, possibly, of course, two of them have to be infinite. And it's affine in each of those pieces. And I don't require the function to be continuous. So it can have discontinuities. So it can be like a piece, and then another piece that doesn't connect, and another piece. So this is t affine. And two examples are, so this kind of popular function is piecewise affine with two pieces. But then you can come up with other examples. So again, this is only a univariate example, so decision tree kind of isn't as meaningful as usual. But decision tree with t-1 nodes will just have its t sawtooth. So this lower bound will also apply to very different algorithms. So for instance, this lower bound also applies to boosting. But you might say it doesn't matter because it's a univariate problem, but still, the result holds. So reasoning about these functions is very easy. So first, if I have something that's s sawtooth, so it's piecewise affine in s pieces, and I have another function which is t sawtooth, so it's piecewise affine in t pieces, I claim that the summation of these two is just s plus t-1 sawtooth. And the proof is just to look at every time the slope changes. So every one of the pieces over here. And I notice that in each one of these pieces, they both have a fixed slope. So I can just count the number of times it changes between the two of them. So that's actually it's s plus t-2 changes. They both agree on the first interval. So then s plus t-1. On the other hand, if I compose the two together, it's s times t sawtooth. And the way to see what goes wrong is, so I compose this with this, so this comes first. So I take the t sawtooth function, I look at any interval, any one of the t pieces that define it. Well, if I take that interval and I map it through the function, I get another interval because it's affine in that piece. But that interval I map to can hit every piece in this thing. So for every interval of the second function of the function you apply the second one to. Sorry, it's composition should be defined the other way. For every piece over here, I get s pieces over here. So together, I get s times t. So, and if I apply an inductive argument to a neural network, this is actually quite easy to see. So what you do is you look at any node in the network. And I take all the functions that plug into it. So if I'm at some layer j right now, all the nodes plugging into it are inductively going to be tm to the j sawtooth. I add together m of them, so I'm going to be m tm to the j sawtooth. I apply my nonlinearity tm times tm to the j sawtooth. So the whole thing is going to be tmj plus 1 sawtooth. That's the inductive step of the proof. So saying it again, a network with a t sawtooth nonlinearity, m nodes in each layer, and l layers is tm to the l sawtooth. And the point of this is that the number of bumps, the number of pieces in the function, grows exponentially in the number of layers, but only linearly in all the other parameters. So this is actually what's going to make the proof go through. We're building these bumps much more quickly with composition than with addition. OK, so this, as it turns out, is basically going to complete the proof of the lower bound. So I'll prove on the next slide a lemma. The lemma just says that if you give me any sequence of 2k points with labels alternating. So the prediction problem is from the reals to 0, 1. You just give me any sequence of reals, and I label them 0, 1, 0, 1, 0, 1, alternate as fast as possible. And the claim is that any t prime sawtooth, so it's piecewise affine in at most t minus t prime pieces, has to have error at least this. Oh, sorry, I should say what it is. 2 to the k minus 2t prime over 3 times 2 to the k. So yeah. So I'll prove that on the next slide. And the reason this completes the proof is because suppose that you have your network structure satisfies this inequality. So if you just plug this in, you get that the error is at least a sixth. And to make sense of what, so this is where I'm going to say the concrete version of what the lower bound actually is. So to make sense of this quantity, let's say L equals 2. So 2 layers. And let's say we're with this, do I put, yeah, sorry, I wrote all this out here. So if I use this thing, which was 0 on one side and identity on the other side, which is 2 sawtooth. So t is 2. And let's say I use 2 layers. Then if I have less than 2 to the k over 2 nodes per layer, error is at least a sixth. If I make it root k, and I have less than 2 to the root k, then I once again have error in sixth. This is pretty rough. I will say, actually, this is very much improvable. So I guess theory audience, the Rockhurster video has this very nice improvement of the switching lemma from, you said it's this Fox, right? Yeah, and so that one actually says that if you just bump down the number of layers by 1, you still get an exponential gap. That isn't implied by this result. So the kind of separation you get from his result over circuits and whatever AC0, it's stronger. Right. OK, so here's how we prove this lemma up here. So I have my t sawtooth function, or I guess I said t prime, and I have 2 to the k alternating points. So because I'm talking about classification, in classification I take everything that's above a half and I make it 1, and everything below make it 0. So all that matters is where I cross 0, where I cross a half, basically. So that means I get a function which is piecewise constant in 2t pieces. The reason it's 2 is because at the discontinuities I can also cross. So that's why it's not t sawtooth to t sawtooth. It's t to 2t. So the discontinuities actually nuke the constant, and the bound is not tight with constants in the continuous case. OK, so now notice that if I just treat each of these intervals as a bin, then the number of bins that get at most 1 point has to be at most the number of bins. So I have at most 2t bins with a single point. And that means that the number of bins with at least 2 points is n minus 2t. So the total number of points that land in bins with at least 2 points is n minus 2t. And the reason this completes the proof is because if you're an interval that gets at least 2 points, they're an alternating label, so you have to make error at least a third. In the limit, it asymptotes to 1/2, but it's at least a third. So I just divide this by 3, and it completes the proof. Sorry, that was the end. OK. So yeah, it's just a counting argument. That's all it is. I thought the proof would be much more complicated. And so you notice that there are no there's no oh, it's not like it holds for certain k and others. It's just that easy. Now let me tell you really quick how the upper bound works. And this one's even easier. So the upper bound is I have to find a function that's either in k repetitions of a constant size network, that's the recurrent case, or it's a k-layer network with k parameters that fits these points exactly. And it's really easy. So I take this function, and I wrote it out tediously up there just to establish to you, if you're doubting, that it is just 3 nodes and 2 layers. But this is the easier way to read the functional form of it. So just a little pyramid. And now the question is, what happens when you compose the pyramid with itself? It's quite easy. So it looks at points that are less than a half, multiplies them by 2. Points that are bigger than a half, it reflects them. So it's literally all it does. It's just it. So, and then by induction. So then I can just take this set of points with alternating labels to be the bottoms and the tops of this function. And then that's really it. One thing that I found kind of fascinating, because it wasn't by design, it was just kind of an accident. So you could argue, I mean, this isn't, I don't know how, okay, you can argue that this is effectively an approximation of a Fourier basis. You give me a k, and I construct these kind of high-frequency piecewise affine functions. And there is a fairly recent survey on neural nets where they also just asserted that Fourier basis is easy for a deep network. Also, the switching lemma, that was parity functions. That's the Fourier basis over the Boolean domain. So I don't know if everyone's doing Fourier bases, because that's the first thing you think of, but I don't know, just interesting coincidence. OK, so we can close from here. So to summarize, so first we gave a couple classical results where we can fit any continuous function with a shallow network. Then we pointed out that the VC dimension, at least, so the number of classifiers we can construct, does not grow too quickly. So it's just linear in the number of layers. And then we gave this case where there do exist functions where you have to blow up the amount of parameters exponentially in order to fit them with a shallow thing. And of course, that doesn't contradict the VC result in any sense, because it is just one class of functions. It's not describing, it's not saying that in every case we can kind of reduce the complexity by logarithmically. There's kind of a nuance that's lost in the VC characterization. OK, so I have a bunch of kind of random remarks that are just things I found very interesting. So at least for this construction, if I use these indicator functions, the result is false. You don't increase the complexity at all when you do compositions. I mentioned this to Sebastian earlier, and he pointed out immediately that I'm using only the univariate case. And I can actually tell you that in the multivariate case, it is slightly different. But already I found it interesting that you have to use something that all the proofs I know for these upper bounds, not just that pyramid function I showed you, but other proofs I know, they need a continuous function. But like I said earlier, that class has infinite VC dimension. So you have to be very careful which continuous functions you use. Oh, sorry, yeah. So this has, oh, I didn't mention this. This is used as a lemma in the proof of the infinite VC dimension for a very specific nonlinearity. OK, so another thing, and this is a result I'd really like. I actually think I'm going to probably try to prove it sometime this month, is so we constructed a single function that we know is very expensive to construct with something that's shallow. The question now is, what are some other ones? And the result I would like to approach is, can we define a notion of independence and rank? So in other words, let's say I just have a grab bag of functions that I can represent efficiently with a multilayer neural network and inefficiently with a shallow network. Is there some other function now, which I can't represent as, let's say, a linear combination or just a composition of these other ones, now that I can throw into this bag, I can kind of keep increasing the set of functions I can characterize? Because we didn't at all characterize all the functions that have L layers and M nodes in each layer. We didn't even remotely characterize that function class. But maybe maybe we can find a couple more of these functions, maybe not just these piecewise affine Fourier transforms, but maybe there's a couple others that together they actually do characterize the entire class. That's what I mean by dense in quotes there. This is something I'd really like to answer. Another thing is what actually is this function? So a lot of you know Leon Batu. I gave actually this talk in Facebook about, I gave a version of these results, some other stuff at Facebook. And Leon, he said to me that he was very fascinated by this pyramid function. And so this pyramid function is pretty funny. So if you take a symmetric function g and look at the composition g composed with the pyramid. So what does it do? If g is from 0, 1 to 0, 1, if I go, so pre-composition, so if I go from 1 to 2 to the minus k, I'm going to replicate g, just a condensed version of it. And then from here to here, so from 2 to the minus k to 2 to the minus k plus 1, I'm going to get the reverse of it. Since I said it's symmetric, I'm going to duplicate it. So this precomposition is going to repeat the function 2 to the k times. So it's like this period. It's like a period operator or a looping operator. So I say that there's prior work. If you know about this Kolmogorov-Arnold representation result, it uses space-filling curves and fractals. And so this is a paper. There are people that claim the results are relevant, but I say actually that it captures a lot of this kind of this interesting structure that's also in this pyramid map. And then, so I think in general there's a lot of room to develop just nice theories about what composition of functions does. So oh, and by the way, I'm not making fun of function analysis because I actually spent way too much of my PhD reading function analysis books and using it. But now I realize, wait, like I really need to know about more than just vector spaces. So, but there are a lot of interesting fields, and maybe during the questions section, which we'll get to in just a moment, people can just tell me about other ones. But I feel like we can just keep doing so much more. So of course, in TCS, there's circuit complexity results. So another family of results that I literally know nothing about, I just found out about from Luca Trevisan's blog, is so in additive combinatorics, they look at the following problem. You give me a group, and I look at a subset of it. Not a subgroup, but a subset. And then if I look at what just happens when I take the group operation, just apply it to itself. So I can take the group, some subset of the group, not a subgroup. So I'll call it S. And I apply all the elements themselves. Call it S squared, S cubed. What is the rate of growth of this thing? So to me, this is very, very similar to this. How many functions do I get as I add more layers problem? So I think there are lots of fields that are attacking this problem of exactly what is this function class as you apply these compositions. I think there could be. So this for me is where this is just a purely beautiful mathematical question, because I still don't understand what these compositions are. And so of course, from our computational perspective, what we really want is some structure that actually helps us design algorithms. Some structure that an algorithm can pull out, something maybe like that correlation thing, but a correlation that works in a multi-layer fashion. So for me, that would be the best. That'd be the best kind of structural result. Okay, we're done.
Questions? Maybe just a comment. So the result that you told us, it's far from the separation in circuit complexity, right? Because here it's just for
univariate.
Not only univariate, but it's not a worst case. In the worst case, it could still be that shallow and deep are the same thing.
Yeah, there could be certain functions that have that property. I just gave one function class.
Yeah. Whereas what the radio did is that he showed that in the worst case there is 4 Boolean circuits.
Yes.
Yeah, okay.
I have to trust you on that. I thought he did not show that, but I just maybe don't know the result well enough. I thought he did something kind of like the switching lemma, where he gave a specific function, which is hard to approximate with one less layer. But maybe I'm wrong. Does anyone know? So to be clear, I thought the result was a specific class. He calls it the SIPs or something functions, where it exactly exists in a depth k circuit. But then if you go down to k minus 1 circuits, you can only get 1/2 minus little o of 1 close without having an exponential blow up in the size of the circuit. That was my understanding of the Servideo result. But you know, yeah, I feel bad saying that because I'm not trying to diminish the result. Like, it's not.
Actually, can we go to your slides on VC dimension? You just went over the right pages. There were two results you said, right?
Yes.
So
Go ahead. You can.
no, I just want to recall.
You want to admire the book cover? Or? That's all I didn't do this very well, did I? I spent more time talking about the book cover than about the result. So
okay, so there was one, and there was one result before. So there was two sigmas you talked about, right?
Yes.
So this,
indicator.
and then there's just the size of the L.
Yeah. Oh yeah, yes. So yeah. So it was this one. This is the answer. So it's number of parameters.
Yeah, if sigma is just
indicator, yeah.
And the next.
And this is if I use that one that is popular now. And the reason I picked this function class was because for this we do have a theta. We do have a tight upper and Bauer. Were you going to ask about what other function classes
no, I just wanted to. So you always have these, like, okay, that's the two numbers or two bullet points below. That was like a multiple choice. Like, okay, this could be that answer, or do you expect something over there, or why?
So you're asking why I thought these were relevant bullet points to include. I could have tried to sneakily construct this talk where I try to make it sound like my result is actually showing that there are tons of these functions where it takes exponentially as many nodes. So if it was true that I always could take any function that has exponential size with a shallow network and compress it down to a linearly sized deep network, that must imply that the VC dimension is exponential, because I'm getting all those functions. So they have to live somewhere. So if my result was not, did that make sense as I explained, or was that? So you can interpret this result as saying that my result, which was for a fixed class of functions, there actually aren't that many of them. There aren't that many of them. Then the second bullet point is because if you look at all the existing bounds, a lot of the upper bounds, not for this function, this sigma, but for many others, actually are quadratic. And I won't call out names because maybe that's unfavorable if conjecture is wrong, but people I rate, way up. They have conjectured to me that it actually is superlinear or super multilinear, so quadratic in some cases, which I have the only intuition I have that might be true is what those people told me. So it might actually be quadratic in some real cases.
So with some sigmas using.
Yeah. Including ones that people care about. Yeah, it's not just pathologies. By the way, and I mean an interesting case is if you saw all my reasoning was doing these little piecewise things, talking about bins, right? Just discretizing. What if that thing is 1 over 1 plus e to the x, which is the sigmoid, which is the common thing people use, or 1 over 1 plus e to the minus x. That thing we can still prove a theorem, but right now the only upper bound there is actually quadratic. Or actually, sorry, that upper bound does not even depend on the number of layers. So actually exhibiting a dependence on the number of layers is often tricky.
Peter Bartlett had a result many years ago.
I couldn't hear, sorry.
Peter Bartlett had a result many years ago saying that in neural networks, the size of the weights is more important than the size of the network.
You mean the magnitude of the weights?
Yes. So can you kind of connect the dots? How does it connect to the results you presented here today?
You mean how does it connect to these VC dimension results, or how does it connect back to my?
Yeah, he showed that the complexity of kind of the class represented by neural nets is dependent more on this is what he claimed in this paper, depends more on the size, the absolute.
Like the L1 norm or something.
Sorry?
Like the L1 norm.
Yeah, the L1 norms of the weights as opposed to the number of the weights. So how should we put it in context here?
Sure. So it's possible that what I'm going to say is wrong because I don't know exactly what he meant by that. But I'll tell you what I do understand. So it depends on what exactly you're giving a bound on. So the VC dimension is a bound on the classification error. If we were, for instance, caring about the logistic loss or the exponential loss or hinge loss or one of these, for these, we should use something like a Rademacher complexity result. If we use the Rademacher complexity bound where we think about the Rademacher complexity of this loss class. So I'm looking at the Rademacher complexity of the loss composed with the predictor. In that case, then the norms of the weights will come out naturally. So if you care about those kinds of problems, for instance, you care about regression, then that quantity is the one that will come out naturally. The reason I do consider it to be apples and oranges is because sometimes you really do care about classification, and these are theta bounds. They're tight. So not only that, there really are cases where you want some and not the other. So one thing I was telling Sebastian about earlier today is that this function, oh, okay, I won't jump to it, but that composed pyramid function I constructed, it's got 2 to the k, it's got 2 to the k up and downs in the interval. That means its Lipschitz constant is 2 to the k. So there are some ways to analyze this class of functions that would just blow up the complexity. But if you care about classification, then that's not the right estimate. So I would say that it's problem dependent when you think about the 2 different bounds, and they are, I would say, kind of apples and oranges. I don't find that answer entirely satisfactory. I just kind of summarized for you the results about one and the results about other. But
I think this is still a very interesting open question, actually.
Yeah.
To understand precisely what is the norm, that characterizes the capacity of these neural networks. This is still essentially open. So what Peter Bartlett did, like I guess 15 years ago, was indeed either for the L1 norm over the entire network or the L2 norm over the entire network. But you could think of things which are much finer because the last layer and the first layer, they shouldn't be represented in the same way in this norm. So, but that's still essentially open.
Sorry, I don't know that result. Was that result like is it showing that if you have a bounded L1 norm, so
right?
not powerful?
So one, you can express the Rademacher, so you can get the dimension-free Rademacher complexity bound if you control the weights of the entire neural network, either in L1 norm or in L2 norm. Just like one layer. This is still true for multi-layers. But you could expect, presumably, to have a much bigger class where you still have a dimension-free bound of the Rademacher complexity, but where the norm is not going to be the same in the last layer and in the first layer. Does that make sense?
Actually, if I can make one more comment here. If you look at the original Rademacher and Gaussian complexity paper, Bartlett-Mendelsohn, there's a very nice Rademacher complexity bound in there that I do not see discussed much. Particularly, I never see discussed in summaries of Rademacher complexity on a 2-layer network. So for a 2-layer network, so one of the big, okay, so I was making it sound like VC versus Rademacher is a question about whether you care about real valued objects or 0-1 objects, basically. But there's another big deal, which is, of course, Rademacher complexity is distribution dependent. And so he has a bound in there that actually depends on sparsity structure a lot. And so then he has a really, really, really nice theorem in there for basically the Rademacher complexity you get is this S log n type effect that you always expect to sparse things. Or if you know what I mean. Instead of being root n, it's an S log n. So that's the number of non-zeros. And so so there is this other benefit of Rademacher complexity that it does allow us to have these nice distribution-dependent things.
All right. Thanks, Matusz.